Hello and welcome to another problem session. Today we have a really good problem here. So in this problem, there is a block here that will slide on this surface up to point P, and after that it kind of falls off. Block leaves and it will go kind of like a curvy path in a parabola. This would be a free fall. It's like a projectile motion at that point. At that point, it's going to be that's the projectile motion. I'm not really drawing properly because it should be a tangent to that path, and this will be tangent at P. Okay, so we're supposed to find this angle at which this will leave the surface. All right, so okay, so we have two situations. Block is here at the very near the top, is a little off center, so that when you let go it starts to slide. So this is little off center. Okay, there are a couple of questions. Why would it slide off? Why not it just continue, follow the sphere? Well, you can see it's going to slide off because initially, maybe over here, at the very top, it's what kind of forces you have? A gravity this way, right? This is the weight, and the normal will be balanced. So at this point, if you place on center, then it's not going anywhere, right? Then it's not going anywhere. If when it's sliding, it's over here, then gravity is still down this amount, but the normal is perpendicular to the surface of contact, right? So normal is this way, and you can see the if you come down like this, come down like this, and come down like this, so acceleration is at that point is made up of centripetal acceleration and tangential acceleration, and these together, net acceleration is down like that. That's the net acceleration. So if you go a little bit further out, tangent has actually, this normal has decreased to a very small amount, but the weight is still going this way. And then if you make this a rectangle, this is the direction of the acceleration. Net acceleration is that direction, in the net force direction. Of course, that's made up of AC and AT, right? Tangential acceleration and AC acceleration. And then when it comes at that point, normal has actually gone to zero. So if I draw the normal out at different points in its motion, over here is that way and that big. If I'm over here, it's kind of decreased. Over here, where it comes out, normal is equal to zero. So that's point P, normal is zero. And at that point, on that point onward, the acceleration, wherever it is going, acceleration is straight down because there's only one force at that point, force of gravity. Is the weight is the only force, so that's the direction in which there's acceleration, net acceleration. Okay, so when we look at this last point P, it's still you can see that this is going in a circular path, and at that point the net acceleration is this way, and because there's the weight, that's the only force, so the net acceleration is that way, and it has a component along towards the center and a component along the tangential. We're not going to worry about that component because we'll look at only this direction of F equals ma in that direction, in radial direction. At this point, let's call it point T, and this is T equal to 0. So we'll look at that, and that will give us a relation between a speed here should be what the speed should be here, because AC is going to be, so if the speed is v here, then it's going to be v square over r is the radius of the sphere. So it will be that at that time t. So at time t, so AC is this, and there is AT which we don't care, and that is actually dv over dt. But we're not going to care about that. So we got AC, and if you look at AC is in that direction, and if this angle is theta and the weight is in that, that's the only force, that's the weight, is the only force in that direction. If this angle is theta, then this angle is theta. Then FC is going to be, weight is mg cosine theta, right? It's going to be, so using these two, we can write down FC equals to MAC, and that gives the mg cosine theta equals to mv square over r, and m got cancelled out. So we have, at this point we do not know what v is and what theta is. So let's call this equation 1. Now we're going to make use of this idea of frictionless. So frictionless at t equals 0 is here, and t equals to t is here. So let me draw another figure, because that can be too cluttered. So it's here at t equal to 0, and it's here at t equals to t. And let's this angle theta. So if I look at how if I say that's going to be a 0 of gravitational potential energy, that's going to be reference. Then when it's over here, it's going to be potential energy will be the distance is r, mgr, and when it's over here at that height, so I need to figure out that height. Well, the whole if this is r, then this one is r cosine theta. So at this level, u at 0 is like this, and u at t is mgr cosine theta. V is 0, so kinetic energy at 0 is 0. V at that point, we assume the speed is v, so kinetic energy at this time is half mv square. And here to here, when it moved, we assume there is no air drag. Such a speed is so low, air drag will be negligible. So the only surface could have done some energy extraction, but because this is frictionless, there is no energy loss here between when it was here and when it was here. So energy of the block at 0, at time 0, equals to energy of the block at at time t. So this one is mgr equals to mgr cosine theta plus half mv square. M got cancelled out, and we want v square over r actually to get the theta. So we want so this is my equation 2, and you can see I can just say v square over r is 2g 1 minus cosine theta. Okay, so multiply by 2 and divide by r and send this down the other side. So this is 2. So put in here. What do I have? I have g cosine theta equal to 2g minus 2g cosine theta, and I bring on this side, and the g's are got cancelled out. So I have a 3 cosine theta equals 2, then cosine theta equals 2/3, and so theta is arc cosine of 2/3. That's the answer. It's a really good problem if you think about it. It's easy to get lost in this AT part. AT has its use in some other questions, but in this question, if I just have to find angle theta, we can just forget about that, right? What could go wrong? Probably nothing here can go wrong, because we are just using this direction as one of the axes along which we're writing this equation of motion. So this I can think of one thing could go wrong now, that we're looking at this angle direction. This direction is a positive direction for us towards the center. So we're looking at that radially inward direction. So maybe I could have made a negative problem here, but mistake here. But as long as you stay in the magnitude, you're probably okay here. In terms of energy, I would say one of the things that tends to go wrong is where to pick where to pick the zero of the energy. I could have picked zero of this, zero here, and then this will be a negative potential energy, and so that may be a problem. You could pick zero here, and then from here you can just say this versus this, but still you'll have to do the same kind of work, and there's some common energy that will have cancelled out. I think as long as you pick a reference convenient, you'd be able to implement this equation for energy quite readily. All right. Okay, so that's all for this. In terms of extension of this problem, how can you extend this problem? You can ask a question like this, see if you can actually do this problem on your own. I'm not going to address this. You let go here, and over here it leaves, and you can ask where does it strike? Having fallen where it left, theta, so you know at what height it left. So this is at 0, and the question is from here to here where it will strike. That's one really interesting question that you might play with. Another more difficult question that you can ask would be, when I'm over here, over here you can ask less difficult question is, what's the speed with which I'm going. So you can actually use this, since you know the theta now, you can go plug in and get the speed if you know the r. So that's not so difficult question. What's the v there? You can ask what's the time there when, if this is t equal to 0, when does it come off? You can ask t. So these are some of the extensions you could play around with you, or maybe you can play with, work with some friend. These are some interesting extension of this problem. This problem is, you'll find this problem in many textbooks. Probably it's also here. Okay. Always don't forget to subscribe to this channel. It helps in the distribution to more people. I'll see you in another video. Bye.